The last talk today. The last speaker today is Sung-Soo Byun from Seoul National University, and he'll talk about spectral moments and Harer-Zagier type recursion formulas in random matrix theory.
Okay, thanks a lot for the introduction, and also I'd like to appreciate to all the organizers for having me here today. Before joining Seoul National, I spent 2 years here at KIAS as a postdoc, so I'm glad to be here back. And today, as in the title, I'm going to talk about certain topics in random matrix theory. In particular, I'm going to introduce a certain observable called spectral moments, and some formula, what we also call the Harer-Zagier formulas in this context. And before the talk, let me first mention that, of course, I understand that we have a quite diverse background in this room, but I prepared this talk in a way that is accessible to non-experts. So, for instance, I didn't expect any kind of background knowledge about random matrices. And I believe you can easily follow this talk. Right, so this is the outline of my talk today. And in the first part, the first part is basically the introduction part. And in the first part, I will focus on the most fundamental and classical random matrices, especially some kind of Hermitian random matrices. And I'm going to introduce what is the spectral moments and classical results in this direction. In particular, I'm going to introduce what we call the Harer-Zagier formula. And then these kind of classical results have been developed and extended in many different directions. In particular, in these days, there are some developments in the context of non-Hermitian random matrices and also discrete deformed matrices. And in the second and the third part, I'm going to introduce some of my recent contributions in this topic. And of course, please feel free to interrupt me whenever you have some questions during the talk. Okay, so let's slowly start. And let me start with the really basic in random matrices. And in random matrix theory, usually the first model we learn from the textbook is so-called the Gaussian unitary ensemble. And actually, like aligning with the general topic, mathematical physics for this conference, let me give some brief remark on the history. So usually we say the beginning of the modern random matrix theory goes back to Wegener in the 1950s. And the idea of the motivation of the Wegener at that time was he tried to describe the energy level of the heavy nuclei. And for some reason, he made some idea that these heavy nuclei energy level can be well described using the certain eigenvalues of certain random matrices. And this particular random matrix is called the Gaussian unitary ensemble. And if we have a look at the definition, actually this definition is more than natural. So first of all, because we want to model some physical quantity, therefore using some eigenvalues, so that we consider the Hermitian matrices. We impose this Hermitian symmetry. And then actually, other than this hermiticity, the matrix model is really simple. So other than this hermiticity, all the other elements are simply given by the independent random variable, especially our most familiar normal distribution. And then because of the symmetry, if we have a look at the eigenvalues, of course, all the eigenvalues are real. And if we have a look at the eigenvalue distribution, if we look at the histogram, and what we can observe is something like this. In particular, in our context, we usually take the large n limit. And then if we have a look at if we increase this dimension, then what we can observe is that this histogram tends to follow certain distribution, which is known as the semicircle law. And this is exactly what Wegener proved in his famous paper in 55. And if we want to make some mathematical statement, we can state this convergence in this way. But the essential point is that the slide, the picture we just saw. So if we consider the eigenvalues distribution after some proper scaling, then it converges to this semicircle distribution, which we now call the Wegener semicircle law. And today, let me explain briefly the original idea of Wegener. And then actually it's quite simple. So the first observation is that if we have a look at so this is our goal. And the first observation is that we consider the moments of this particular distribution. And actually, this is a high school exercise. So if we use the proper, integral by parts, what we can observe is that if we take the moments of this distribution, and then of course all the odd moments vanish because of the symmetry. And then if we consider this even moment, then what we can compute is that it is given by the Catalan number. And then this is actually the key idea. And the idea of Wigner is considering the finite n version of the observable for these particular random matrices. So this is exactly the definition of the spectral moment. And in particular for this Gaussian unitary ensemble, the definition is given like this. So we consider this matrix model and consider its power P, and then take the trace and consider the expectation with respect to all the randomness we have in defining the matrix model. And of course, we can write down this as the expectation of the moments of the eigenvalues. And this is the reason why we call this as a spectral moment. And then what we're going to prove in this paper is essentially what is the asymptotic behavior of this quantity. And then this is known as the moment counting method. And actually what he proved is that if we consider this moment and its leading order, it grows as n with this particular order. And then the important thing is that the leading order converges to the Catalan number. And then actually this holds for any moments p. That means, and if we have the convergence of the moments for any power p, then there is a nice way to recover this limiting density itself. So this is the way first we're going to obtain the semicircular law using these spectral moments. And then if we think about how we compute this kind of quantity, and then if we have a look at this, then this is some matrix power. And if we take a trace, then it means this trace of matrix power contains a bunch of product of the elements, in this case, some Gaussian random variables. So this expectation is basically big summation of product of p Gaussian random variables. And then we can compute this expectation of the product of Gaussian random variables using so-called Wick's formula. This Wick's formula basically gives us some nice graphical realization of this expectation. And the most important part is why we encounter this Catalan number. And then the reason is as is written here. And so each element in this big summation can be written, can be identified with certain pairing of these two p vertices. And each pairing gives some contribution to the spectral moment. And then the leading contribution of this quantity somehow comes from the pairings which have these non-crossing properties. And then it's a well-known combinatorial fact that the number of non-crossing pairings of 2p vertices exactly coincide with this Catalan number. So that's the first way we encounter this Catalan number. And so that we can recover the semicircular law. All right. So for instance, we can explicitly write down these spectral moments for some particular small values of p in this form. So what this moment counting method tells us is that, so this is the leading order. And then the coefficient of the leading order is basically given by the p's Catalan number. And also as a side remark, so if you sum all the coefficients, and then you can see that this coincides with this quantity, which is the total number of the complete pairings. Okay, so this was done by Wigner, but somehow from these kind of formulas, we can observe something. So the first thing we can observe here is that these spectral moments is given by some polynomial in n. And actually, the structure is quite simple. So the structure is these are either odd or even polynomials. But somehow, for some good reason, we also want to understand not only the leading order, but also this polynomial itself. And then, and the most natural thing we can hope about this kind of formula is we may expect some kind of nice recursive formula for these polynomials, for this sequence of polynomials. And then this is exactly the result due to Harer and Zagier in this quite well-known paper. Well, actually, I believe there are many other people who can have a better understanding than me about this paper. But actually, in this paper, what their original motivation comes from more like the Taichung theory. So they try to compute some Euler characteristics of a certain mapping class group on a compact Riemann surface with genus G. And then for somehow they used some ideas which basically from random matrices. And then their main result follows exactly from this kind of recursion formula. So if you have a look, then actually a priori it is absolutely non-trivial that even there exists certain this kind of finite term recursion formula. And then, but it turns out that it is. And so this is a recursion formula in P. And somehow surprisingly, we have this relatively simple three-term recurrence formula, from which we can also obtain all these kind of polynomial expressions. And then another remark in this direction is actually, so we know, so the leading order coefficient has a very nice combinatorial meaning. As you know, so this Catalan number has more than 200 combinatorial meanings. But actually, not only the leading order, but also the coefficients of these other, the sub-leading coefficients also have some nice combinatorial realization, which is actually also known as the genus expansion. Well, simply speaking, in this case, actually, these coefficients also give solve some counting problem, especially on a compact Riemann surface of genus G, where this number of genus correspond to the expansion, the order of the expansion in 1 over n squared. So this is one of the reasons why people call this as a genus expansion. And actually, this notion of the genus expansion was already introduced in physics in the 70s by Toft. And actually, there are also many other different names of the genus expansion. Sometimes it's called like topological recursion. And also usually in random matrices, it is also called loop equations because we have some another graphical realizations. And also from more like field theory point of view, this is also known as the Wald identity. But anyway, so this we also have some expansion. So the point is that in any case, usually we want the case when n is large. And then these coefficients also have some nice meaning. Okay, and to prove this kind of recursion formula, actually we have there are quite a lot of different proofs, and one of the most natural proof I think is due to Hager and Jensen. Both are from Copenhagen, and most natural I think one of the most natural proof is just consider the moment generating function, and then actually both of these two people are quite well known name in operator algebra community. And then what they prove is that this generating function satisfies this kind of second order simple ODE. But the good point here is that in this case, it is linear. And also the coefficients are given by polynomials. That means if we recall that this generating function really generates the spectral moments, then this kind of differential equation indeed gives rise to certain recursion formula, which exactly coincides with this Harer-Zagier formula. All right. And then so far, let me recall. So far, we consider the most natural random matrices, the random Hermitian matrices. So we consider these Hermitian matrices with our complex Gaussian entries. But of course, we can also consider a real counterpart, a real recursion of this unitary ensemble, which is called the Gaussian orthogonal ensemble in this case. And then in this case, the definition is basically same, except that in this case, we only consider the real Gaussian instead of the complex Gaussian. But actually, as usual, if we consider the real elements instead of the complex elements, usually this makes our life a bit more complicated. And also, this is also the case if we consider this orthogonal ensemble. But here, the point is that for these kind of variants, what we also want to understand is basically the same objects. We want to understand same kind of the spectral moments, the same observer. And what we can also not so difficultly obtain is, again, the moment counting. The idea of Wigner also works. And then what we observe is that the leading order is at least the same with the GUE counterpart. It is also again given by the Catalan number. But if we have a look at some examples, we can easily observe that the formulas becomes a bit more complicated. For instance, in the previous slides, for the spectral moments of the GUE, is polynomial in N, and is in particular, it is either even or odd degree polynomials. However, actually, for this Gaussian orthogonal ensemble, if we consider this real element, then it is no longer either even or odd polynomials. And also, but still, we may also ask whether there are similar kind of recursive formula for the spectral moments. And then this question was addressed by Ledoux in 2009. And the difference is that actually, as I mentioned, usually the situation becomes complicated. And it turns out that we cannot expect, again, 3-term recurrence. And in this case, what Ledoux found is this 5-term recurrence formula. And this is probably the simplest recurrent formula we can expect. But the proof of Ledoux is basically along the same philosophy of these Danish mathematicians. And Ledoux also considered this generating function. And basically, he derived a certain differential equation for this quantity. And eventually, he could derive this kind of first-order differential equation, which again gives us this nice recursion formula. But instead of the 3, in this case, 5-term recurrence. Okay, so this, and also, as I mentioned, so these two matrices are basically the most classical random matrices. And there are really a lot of further directions, further studies of this kind. And for instance, there are also notion of the orthogonal polynomial ensembles. And also, actually, these GUE matrix eigenvalues can be realized in 2 different manners. One is as a Coulomb gases, 2-dimensional Coulomb gases restricted on the real line. Or actually, if you know what is the notion of the Slater determinant, and actually, basically, GUE eigenvalue can be identified with the 1-dimensional free fermions. And then we can also consider the higher dimensional analog. And also, usually, and also these days, what people study really a lot is non-dimensional random matrices. And also, there are also some good physical reason to study Q different version. And actually, also, we study these kind of spectral moments, not just for fun, but also we have a good motivation. So for instance, actually these spectral moments, the analysis of the spectral moments itself can be used inside the random matrices, random matrix theory. For instance, to prove certain universality or like counting, attacking counting statistics problems. And actually these also finds applications not only in random matrices, but also in other research fields. For instance, in the context of this non-commutative geometry, or like time series analysis, as well as so-called tau function theory. And then, as I mentioned, so in particular, among these topics, I'm going to focus on these 2 particular models in the next part. So the summary of the first part, where we have some classical random matrices, and with good reason. For instance, because we want to understand the eigenvalue statistics, we consider the spectral moments, which is basically the most simplest linear statistics. And then there is some nice way to derive the recursion formula, which we call the Harer-Zagier formula. And there are also some further developments. Okay, so this is the end of the first part. Any questions so far for this introduction part? Okay, then let me move on to the second part. In the second part, I'm going to introduce what is has been studied for non-Hermitian random matrices. And as before, let's begin with the most simplest random matrix we can imagine. So in this case, we essentially drop out the symmetry. And then in this case, we consider the similar matrices. So we consider some matrix, but in case of the symmetric matrix, in this case, we assume that all the elements are basically independent, in particular, independent Gaussians. And then as a side remark, so we discussed this Gaussian orthogonal ensemble. And actually, this Gaussian orthogonal ensemble is nothing but just the symmetrization of this matrix model. So this matrix is known as the Ginebra matrix, named after Zhang Ginebra. And in particular, because we again consider the real Gaussian, so we call this a real Ginebra matrix. And sometimes we denote this in this way. And as a counterpart of this Wigner semicircle law, we also have some nice distribution, which is called the circular law. And again, if we have a look at the eigenvalues, then of course, because of the lack of the symmetry, the eigenvalues are now in complex plane. And as before, if we increase this dimension, what we can observe from these simulations is that the eigenvalues tends to be uniformly distributed on the unit disk, which is known as the circular law. And here, actually, there is a very special feature when we consider this real Gaussian. And the special feature here is that the eigenvalues is basically the roots of the characteristic polynomial. And then in this case, the characteristic polynomial is some random polynomial with real coefficients. That means, of course, the eigenvalues come in like conjugation, complex conjugate pair, or it can be purely real. So one nice way to easily observe the existence of the real eigenvalues is we intentionally downsize the matrix dimension and consider a lot of samples like this. And then we can clearly see that there exist certain real eigenvalues, which is actually also known as the Saturn effect, coined by Alan Edelman. And then, so for some reason, actually there is also some good motivation to study these real eigenvalues. And then in this case now, we only focus on the real eigenvalues of these asymmetric random matrices. And then as before, the quantity we consider the same as before. But the difference here is that in this case, the total number of real eigenvalue is now given by some random number. So it is again, it's basically given by some random variable. But still, what we consider is basically the same observable. So we consider the spectral moments. But as you may guess, in this case, the study becomes significantly more complicated because in this case, we also have some randomness in the total number. For instance, if we consider the zeroth moment, if p equal to 0, then p equal to 0 gives basically what is the expected number of real eigenvalues. And then even this problem is highly non-trivial, and which was solved in 1994. And in this paper by Edelman, Coulson, and Schrupp, what they obtain is basically the zeroth moment. The expected number of these real eigenvalues can be written in this particular and very precise form, which depends on either the dimension is even or odd. And also actually, also later in a also very nice paper by Forrester and Nagao, they also found a more general formalism to derive such a quantity, which can also be further extended. So they, let me just mention the keywords. So they develop so-called skew orthogonal polynomial formalism, which can also be used to study not only the expectation, but also variance, for instance. Anyway, so this is the quantity we want to ask. And then, but still, somehow, other than this zeroth moment, the general spectral moments has not been investigated. So in a recent work by myself with Peter Forrester, what we obtain is as follows. So we actually consider some, we can actually allow P can be a complex number. But in any case, so we obtain this formula of the spectral moments given in terms of some special function, hypergeometric function. Actually, I'm not going to, so if you are not familiar with the hypergeometric function, you can just consider it as some well-known like Gauss series expansion. And then actually, and also if p equal to 0, this expression can be reduced to 2f1, and which exactly gives this formula. And also, what we also could show is, in this case, we also have analog of the Harer-Zagier type formulas. And again, it's actually quite surprising because in this case, even though the spectral moment itself is way more complicated, but in this case, we can also write down the three-term recurrence formula. And side remark, actually, so we first obtain, we actually independently obtain these two formulas. So even though we can expect this hypergeometric expression may yield some nice recursion formula, but that's not the way we derive this formula. And then rather, the way we derive this formula is we again consider the generating function and first obtain this differential operator, which gives this recursion formula. Okay, so this is the result for the most classical asymmetric matrices, Geneva matrix. But actually, we can also make some nice connection with these results with the previous result I introduced in the introduction part. And then there is a nice interpolating model we consider, which is called the elliptic Geneva matrix. And then, so in this case, as I mentioned before, if we consider the Geneva matrix, and if we consider this symmetrization, then it gives this Gaussian orthogonal ensemble. And then the nice way to interpolate these symmetric and asymmetric matrices is as follows. And for this, we first consider this symmetric and anti-symmetrization. And using some parameter tau, we basically consider these linear interpolations. And then actually, when tau, this parameter is equal to 0, then it's again the Geneva matrix, so that we have the circular law. And then the reason why people call this as an elliptic matrix is that it actually follows the elliptic law. That means, in this case, for general tau, the eigenvalues of this kind of matrix tends to be distributed in this ellipse, with actually major axis 1 plus tau and minor axis 1 minus tau. And as you can see, when as tau increases, then this anti-symmetric part is getting smaller, so that what we can also observe is that the eigenvalues is more close to the real axis. And also for this particular distribution, there are also many things known. In particular, some kind of universality was also shown in this paper. And also, when, in particular, in the extremer case, when tau equal to 1, then there is no anti-symmetric part, so we can recover this GOE matrix. And actually, this elliptic matrix was also introduced in the physics community in the 80s, mostly because of some, because this matrix has some application in the quantum kernel dynamics. But anyway, from the mathematical viewpoint, this matrix itself is also quite natural. And we can also ask exactly the same kind of question. Because of the same reasoning, we also have some non-trivial amount of real eigenvalues. Yes, and again, the observable is essentially the same. We consider these spectral moments. But in this case, as you may expect, the expression of these spectral moments becomes quite more complicated. Nonetheless, after in this another work by Forrester and Nagao, they at least obtained the zero spectral moments, which is given in this manner. So actually, so this is given in terms of the big summation of a hypergeometric series. And actually, there is no further way to simplify this formula. And yes, and this is at least the zeroth moment. And what we can also ask for this model is whether we have some nice recursion formula. And the answer turns out to be true. But actually, compared to this Geneva matrix, where we have surprisingly simple three-term recursion formula, in this case, we have surprisingly complicated recursion formula. So it turns out that in this case, we need 11 terms to make this recursive formula. Well, this was done by myself in another paper. And well, this is even quite complicated, but still, we can explicitly write down all the coefficients. And also, again, the idea is pretty much similar. The idea for this recursion formula is we again consider the corresponding generating function. And in this case, as far as I can see, the most simplest differential operator we can find is the 7th order. So at least in this case, actually, but one thing I can mention here is that I still believe there might be some better, simpler recursion formula for this particular model. But actually, it is really far from being obvious to derive whether it is this optimal formula or not. But still, this formula gives some nice interpolations. In particular, as I mentioned, so even though this is like 11 term we need, but as we saw in the extremer case, for the Geneva matrix, we only have the 3-term recurrence. And then in the other extremer case, when tau equal to 1, where we have the symmetric matrix, in this paper of Ledoux, we have this 5-term recurrence. And for these two extremer cases can also be recovered from this general formula. Because a lot of coefficients become trivial. And also, in some sense, we can also naively expect maybe this generating function is probably optimal. And the reason is that, at least in this case, if we take the tau equal to 1, the symmetric limit, then what we can observe is that the 7th order differential operator can be reduced to some 4th order differential operator exactly in this paper. So at least we have some understanding about this, for this general interpolating model, we have at least the existence of certain recursive formula, which interpolates this recursive formula of previously known. Okay, so this is the end of the second part. The message of the second part is summarized as follows. So also, for many reasons, these days people consider asymmetric random matrices. And then also for the asymmetric random matrices, we can ask exactly the question of spectral moments. And then only recently, based on some like knowledges we have had so far, we can also compute some spectral moments for the most classical asymmetric matrix, and which also have some nice recursive formula. And also we can even consider some interpolating matrix model, which interpolates the classical formulas in asymmetric matrices with symmetric matrices. Okay, so this is something we understand about the spectral moments for non-dimensional random matrices. And in the last part, I'm going to introduce what people call this Q-deformed model. So actually, this Q-deformed model is really the Q-analysis version appearing in many different areas. And also this matrix model was originally studied in physics community, which I will try to explain. Okay, but still to explain this model itself, we need to revisit the classical matrix once again. So let me remind the first slide of this talk. So the first model we consider is this Gaussian unitary ensemble. So these Hermitian matrices with these nice independent Gaussian random variables. And then to explain the Q-deformed version, let me explain first some basic integrable structure. Well, actually, as I mentioned, we can also extract some distribution of the eigenvalues itself from this matrix model, which is given as follows. So, where this actually follows from the Weiss formula. So, using the Weiss formula, if we compute the Jacobian, And then we can extract that the eigenvalues of this particular matrix has this joint probability distribution. And this is the reason I mentioned that it is basically the Coulomb-Gauss model with this Coulomb interaction in 2D, but restricted on one-dimensional because we have the Hermitian matrices. And also it has a nice induced measure coming from the Gaussian array. And also, as I also mentioned, so this is exactly the Slater determinant of the free fermion in the harmonic trap. And anyway, so we, from this integral structure, we can analyze the spectral moment once again. And for this particular purpose, we consider the density, the kind of the average density of these eigenvalues at finite n. So essentially, this density means we integrate out n-1 variable from this quantity. And then if only one variable it remains, then this is basically the average density of the finite n eigenvalues. So what we expect is basically this smooth density becomes close to the Wigner semicircle law. But the good point about this realization is that we can write down the spectral moment using in terms of this quantity. So actually, this is nothing but just write down this expectation, the definition in this way. So essentially, if you consider the definition of the spectral moments, we need n-fold integrals. But in this case, we first perform n-1-fold integral and consider the last integral. But one good thing is that we can particularly use this particular structure. And then eventually, what I want to say is that we can write down this density in quite a concrete manner. In principle, so we can, let me first show you the formula. So we can write down this density in terms of this Hermitian polynomial. So first, we consider this classical Hermitian polynomial, and then this density can be written as a summation of this product of square of this Hermitian polynomial. And that I can also mention how to do this. So, our mission is basically integrate n-1 variables of this from this expression. And the first idea is we write down this, we first observe this is basically the Mandelbrot determinant. So this density distribution itself can be written as a certain determinant of matrix. And then probably some of you know, so there is a nice formula interchanging the integral and determinant, which is known as the Andrei formula or Cauchy-Binet formula. And then essentially we can integrate this integral with the determinant. And then our quantity can be written as a determinant of some large matrix whose elements are given by certain integrals. And then these, to compute this determinant, the best, simplest way is to choose some proper basis so that this matrix becomes diagonal. And the proper basis here we means if we choose the orthogonal basis with respect to this measure, then we can make this as a diagonal matrix, which eventually gives this formula. So this is the reason why we need the Hermitian polynomial. And then, so because we need to integrate this quantity one more, then what we need is this particular integral. And this integral, there are also many ways to compute this. And actually, one of my favorite is using some nice combinatorial ideas that I will introduce later. And then using this, if we again plug in this formula, then we can explicitly write down the spectral moment in this manner. Okay, then now I can explain what is the Q-deformed model people consider in this context. And for this purpose, let me briefly recall what is the Q series. Well, actually, the definition of the Q series is actually not so important for today's talk. But essentially, you can think of Q analysis is a kind of mathematics where instead of the integer, we consider the weighted version of the integers. So instead of like 1, 2, 3, so we consider 1 Q square extra. And then we can also consider the notion of the integral and derivatives. And when we take the q goes to one limit, then we recover the usual continuous mathematics. And then, for instance, you can see this is the definition of the q derivative. And then if we take this q goes to 1, then we recover the usual derivative. And then its inverse operation is called the Jackson integral. And it's written as an integral, but it's essentially the infinite summations involving this q, this parameter q. And then this is again the Hermitian polynomial, the another definition of the Hermitian polynomial. And then so we can define this polynomial using in terms of this three-term recurrence formula. And then, as I mentioned, this is the orthogonal polynomial with respect to this Gaussian measure. And then the Q version of this matrix model, here we need the simplest way to define this is using the Q Hermitian polynomial. And then this is the Q analog of this Hermitian polynomial. And then instead of this n, we basically consider the Q analog of the integer. And then in this case, it is also known that it satisfies some orthogonality with respect to this Jackson integral. And then actually, as I mentioned, when we take a proper q goes to one limit, when we take the continuum limit of this q Hermitian polynomial, then this formula, after proper scaling of the this argument, then it really recovers this classical Hermitian polynomial. And then, as I mentioned, so this is the density of our GUE matrix, and the spectral moments can be written in this way. And then, so actually, the actual definition of this Q deformed model can be defined as a certain point process lying on a Q lattice, means instead of the full real line. But for our particular purpose, we can define its density itself using as a Q analog of this classical formula. And then for this particular Q deformed GUE model, we also consider the spectral moments. But somehow, even though this spectral moments is a very classical object in random matrices, and also Q analysis is also quite a classical object in math, but somehow these spectral moments of the Q analog of the GUE has not been investigated. And in a paper by myself with a collaboration with Peter Forrester and also Jae-Sung. Actually, Jae-Sung he is currently a postdoc here at CMC fellow at KIAS. And we obtained this explicit formula, explicit evaluation of these spectral moments using in terms of this basically Q combinatorial identities. And actually, let me first give you some remarks. And as I mentioned, if we properly take the Q goes to one limit, then we can recover again the classical spectral moments. And also, actually, this is not the first evaluation of the spectral moments. And actually, prior to our work, so this kind of object was studied in this paper by these physicists. And actually, they also have another like good physical motivation, and they call this as a quantization of the Harer-Zagier formulas. And also, another paper by Peter and his other colleagues, they also obtained this formula. But actually, what they used is the symmetry function theory, basically the Schur function expansion. And then, if we use this symmetry function theory, then what we obtain is actually certain alternating sum formula. But for our particular purpose, it is way better if we have this. If we have the positive sum formula, that I mean, if the summands are all positive values. And actually, I really like this result because especially where myself and Peter, we worked a lot about random matrices. But actually, this particular collaboration with Jae-Sung, he's not from like my probability community. He's from like algebraic combinatorial community. But after some discussions, we eventually found that some techniques Jae-Sung has can be really helpful to study some problem we want to study. And then one nice, let me explain these particular ideas. This is just a quick idea about some further ideas that I usually not use. And then, so this orthogonal polynomial from algebraic combinatorial community, they consider this as a certain linear functional of this form. And then, in general, we have a nice three-term recurrence formula of these orthogonal polynomials. And then this is the point. There is a nice combinatorial model computing associated to these orthogonal polynomials, which is called the Motzkin path. And this particular Motzkin path allows us to compute this kind of quantity. So in short, this kind of quantity is something we need to compute our spectral moments. And this quantity can be computed using in terms of this path counting method. And also there is a very nice survey paper about these combinatorics of orthogonal polynomials. And then, so as I mentioned before, for the classical GUE spectral moments, what we need to compute is this integral. And then this particular integral, we can also compute using our analysis, like complex analysis tool. But if we consider this Q version, of course, our like contour integral type analysis tool cannot be applied. But still, eventually, using this path counting method, and actually, we also need one another combinatorial trick. So we found some nice matching problem that we can really compute this quantity, so that we could compute this particular integral we want to study. So this is basically the way we obtain this positive sum formula. And as I mentioned before, so if we use this Motzkin path counting method, then what we eventually obtain is always the positive sum formula. And well, one of the reasons why we really like this positive sum formula, the reason is that the reason goes back to the original motivation we have discussed. So original motivation of beginner studying these spectral moments is to obtain the limiting density, the semicircle distribution. And then we also want to do the same thing. That means we want to analyze what is the asymptotic behavior of this quantity. But as you may easily expect, with this alternating sum formula, it is way more complicated to obtain this asymptotic behavior. But using this, we could do this. So in short, in this study, in this Q version, we need to take a particular scaling of this form. And then in this case, what we could do using our this positive sum formula is we could derive this asymptotic behavior of spectral moments. Of course, you don't have to care about these particular formulas, but this is exactly the genus expansion analog for the Q version of the GUE. And here is a nice plot for this genus expansion, its coefficients. And we can also numerically check that our computation is really correct. And then as a consequence, as I mentioned before, if we have these, if we have some good understanding about the spectral moments, then we can also derive the limiting density. So you can forget about these particular notations, but the main message here is that in this Q series, we can also derive the limiting density when n goes to infinity, which is given like this. But here it's much better to just see the graphs. And another surprising fact we observe from this formula is that it turns out that there is another phase transition. So what we could observe is that depending on this parameter lambda, we have some critical value log 2. And before this critical parameter, when lambda is close to 0, then that means it is more close to the continuum limit. Then we have this vanishing density at the edge of the spectrum. And in the other case, we have these two non-trivial peaks in this density. So actually, this is very unusual case where we have this non-smooth kind of density for certain random matrices. And we still believe this is some unique phenomenon in when we study the Q analysis. And another another remarks, and actually, so as I mentioned, so if we take lambda goes to 0 limit, then it actually recovers the Wigner semicircle law. So this density we found in this paper is really the Q version of the Wigner semicircle distribution. And also, this is also the first result regarding some global statistics of discrete models. And on the list, actually, there were also some earlier works about the local statistics. Actually, the local statistics is also closely related to like some other universality phenomenon, especially the KPZ universality classes. But actually, these local statistics we can do without the knowledge of the global statistics. So this was there are also some works in this direction. Okay, so so let me make some summary. So the main message of today's talk. So the first message is the spectral moments of random matrices is certain observable. Basically, it's really the moments of the eigenvalues. And for some good reasons, we want to have some good understanding about these guys. And then actually these are classical objects in random matrices, goes back to Wigner or Harer-Zagier. And then recently, actually not only recently, so far over the past few decades, there have been a lot of developments in this direction. In particular, recently, in the context of asymmetric random matrices, especially their eigenvalues, or Q different version of these discrete ensembles, we also have some understanding about the spectral moments. Okay, so this is what I want to talk about today, and thank you a lot for your attention.
So to me, it seems like what we call the spectral moments is given a random matrix, you look at the expectation value of some polynomial in the eigenvalues.
Yeah, yes.
I wonder whether you ever consider expectation value of other symmetric functions.
Yeah, exactly. So actually, this is a really good question. Actually, if we consider, so exactly, so that's the reason. If we consider some general function, let's say f, some general function f of the eigenvalues, then this is called the linear statistics. And people also consider a lot of this, a lot about this linear statistics. And then, so in that sense, actually, the spectral moment is the particular linear statistics where this function f is polynomials. And then also for the linear statistics, we study, like in probability, we usually study like law of large numbers and central limit theorem, this kind of direction. And then, and another reason why spectral moment is especially important is that in some cases we consider this polynomial approximation of this general linear statistics. So in that sense, the spectral moments provide some nice basis for general study. Yes.
Have you tried considering other symmetric functions?
Yes, actually, so yes, symmetric function, but yes, in slightly different context, yes, we consider some other symmetric functions, which is actually more close to the, actually, even though I didn't present that today, but you know, another recent work with Peter, what we studied is when this test function is some symmetric function, and we make some connection with the McDonald polynomial theory. So that's, and in short, yes, we also consider that. Yeah.
Gaussian unitary case, the number of
Mm-hmm. Yes. Yeah. Mhm.
Five, but the
It's for differential. Yeah.
I cannot remember tell a differential equation
Yeah. Yeah.
why for application
Yeah, said that I can explain. So actually, for that we can just have a look at this. Even so, if we have a look at this, so if we have some differential equation of this generating function, and then this is really the idea in our first year OD class. So if we expand all of this, and then this is really the important. So the important thing is that we have the linear differential equation, and also the coefficients are all polynomial in T. Therefore, if we expand all of this in this way and just plug in these guys, and if we compare the coefficients to make this differential equation, then this gives some recurrence formula. And here it means the number of recurrence formula depends not only on this differential order, but also the polynomial coefficients here. And then here we have like t power 3. So that basically it gives this three-term recurrence. And in the yes, in this case you can see we have like t5 and also the operator is 4. So this eventually gives this 5-term recurrence. So and also the same thing also can be applied to general case. So we have like 7 other big differential operator, but good thing is that we again linear and polynomial coefficients, from which we can extract this recursion formula, which turns out to be 11 order. Yeah.
Can I actually, in the viewpoint of Dyson,
Yeah.
There's a drink type.
Yeah, sure. Yeah.
About the simplification.
Yeah, it's also a good point actually. So it's a really good point actually in this particular paper of Ledoux. So actually, it's really okay. Even though it says it's only Gaussian orthogonal ensemble, and actually in this paper, Ledoux also found the recursion formula for Gaussian simplicity ensemble when beta equals 4. And actually, also another point I can make is actually this Gaussian simplicity ensemble also has a 5-term recurrence relation. And also, actually, there is also some mixed recurrence relation if we consider Gaussian orthogonal and simplicity ensemble, because there is some kind of duality between orthogonal and simplicity class. So actually this mixed recursion formula gives actually 3-term. So if we consider both moments of the orthogonal and moments of the symplectic ensembles, then we have some further simplifications. It's also possible. And also, yeah, there are also many other things I can mention. So in particular, actually these formulas all of these can be related to the symmetry functions. So in particular, in general, because you mentioned, so this for general case, for general value of beta, it corresponds to Jack polynomial. But in case of this unitary ensemble, it corresponds to Schur. And in case of the orthogonal or symplectic case, it corresponds to Journal polynomial. So there are some further relations. And yes, and also, yeah, even though I mentioned only like beta 1 and 2, and also there are counterparts of the result for beta equal to 4. Yeah.
Can I wonder at the recently interesting point the non-Hermitian case?
Yeah.
Can you ever think about this non-Hermitian case?
So you mean the non-Hermitian matrix with symplectic symmetry, or?
Yes, I think that okay. I think the unit. I'm not sure. Recently, there is an interesting point that we're from the start with based on topology and then work out these kind of things. To study what the spectrum, etc.
Yes.
I'm not sure about the technically.
Mm-hmm.
I think recently there's interesting non-Hermitian, Hermitian work out.
Yeah, exactly. So yeah, yes. So actually, okay, so in the second part, I discussed this asymmetric random matrices. Actually, so basically the counterpart of this orthogonal ensemble. But actually the counterpart of the unitary ensemble, this non-Hermitian random matrices like complex Ginevra matrix, has been studied really a lot. So it actually exactly corresponds to these two-dimensional Coulomb gases. And there are, yes, a lot of studies in that direction. Yes.
After introducing the Q analog, to see the asymptotic behavior, we have Q equal to exponential like lambda stand. Could you explain why we do so?
Yes, also good, very good point actually. So as I mentioned, so this is a bit technical and difficult to explain this point process itself, but essentially, so here, so we take this particular limit. It means so because this is so okay. So in the continuous case, the eigenvalues are in the real line. So the eigenvalues can be any point in real line. But actually, in this Q deformed model, it is eigenvalues lie on a Q lattice. So there is only like only particular like lattice the eigenvalues can lie. Therefore, actually, if we just consider Q fixed, then there is not the notion of a proper density. Because it's the density at a given lattice is basically some combination of the atomic measure. So that means when we consider this Largian limit, we also basically what we consider is the scaling limit. The scaling limit, so basically Q goes to 1 in a proper scale. So what physicists actually already discussed is this is a proper scaling we need to consider. So in short, this is really the scaling regime which makes the limiting density make sense. Yes.
Except that the original version of this recursion formula is geometry.
Yes. Yes, it's also a good point. So that's actually not the best question I can answer, but still, for instance, okay, so for the Q deformed, it's actually kind of, there are still kind of conjectures regarding that, but at least for the most classical version, so this Gaussian orthogonal ensemble, so the original paper of Harer-Zagier, they consider the Gaussian unitary ensemble, but if we consider this Gaussian orthogonal ensemble, there is also a counterpart of the geometric interpretation where we consider the oriented surface. So, and there are this notion of like geometric counterparts, but in general, it's still under investigations. Yes. So actually, so one comment is that actually for this Q deformed version, there is some conjecture about the geometric interpretation of these expansions, but that part is at this point is far from something we can prove. Yes.
Who is conjecture?
Say again?
So you said it's conjecture.
Yeah.
Who is conjecture?
I'm not so sure whether there is a well, at least the paper I mentioned, this quantization of the Harer-Zagier formula, they also have some geometric interpretation for this kind of model. So maybe the conjecture was originally due to them, but I'm not completely sure. Yeah. Yeah. Mm-hmm. Also good question, but not maybe, but not completely sure as far as I know, because actually, so for this differential equation is at this point is really the tool to drive us some kind of recursion formula. So yeah, short answer is maybe, but not sure yet. Yes.
further questions? If not, then let's start the speaking.
Thank you.